What's up? My name is Matthew, and in this video we're going to talk about the law of cosines. And this will be a shorter video. We'll look at the two different scenarios where the law of cosines is appropriate, and then there's one last little sort of subtopic called Heron's formula, which will help us find the area of a triangle that is not a right triangle, an oblique triangle. Let's have a look. The first thing that we see in these notes is a oops, my pen is not enabled. Is a note about when we should use each of these two different formulas, so to speak, the law of sines and the law of cosines. And I don't ever remember these. I was talking with a student today about calculus. And he said, how am I supposed to know when I do this really strange form of substitution? And I said, well, what are the other techniques we have available? And he said, well, there's this kind, and then there's this kind of substitution. I said, well, if you look at a problem and you try those two and they don't work, maybe then you should try this third sort of unusual type of substitution. And he said, yeah, that sounds like a good idea. Maybe it's not the most efficient, but we've got a visitor. Let's get this out of the way. Oh, she's purring for us. Are you happy about math this evening? Mm-hmm. What do you think? You want to be... Where do you want to be? Want to be up here? You want to just hang out up there? Sophie's going to teach the rest of the lesson. So my point is that maybe we don't actually need to know when we should use one of these sort of tools versus the other. Maybe we should just try one of them, and if it doesn't work, or it seems like there's not enough information to end up using that particular law of sines versus law of cosines, then we switch over and use the other one. I've already talked in the previous video about how the law of sines is fairly obvious as far as when you're supposed to use it, because you need to have a pair of information, either an angle and its corresponding side measure. Well, not either. You need to have an angle measure and its corresponding side length in order to use the law of sines. In the case of side, 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 which I've written down under the law of cosines, definitely you're not going to have a full pair because there's no angles listed in that situation. So let's go in and have a look at some actual examples. Hey, your claw is digging into my neck. Be careful. Ow. What are you... You're such a spaz. Well, before we get to examples, what's the actual law of sines? These are the three, laws of cosines, and I'm going to have to refer back to these because I don't memorize this kind of stuff, as you know. I'm also not going to spend time on the proof in this video, but undoubtedly you could find that content somewhere else. What are you clawing at now? Be nice. So our first situation is the side angle side triangle, and let's actually have a look at it. So here we can see that the angle is in between the two sides, just as you would suspect with side angle side. And the law of cosines is appropriate here because you can see that we don't have this full pair of information, the A values. We don't have the full pair of values for the B, and the C is missing the angle measure. So there's no way that we could use the law of sines. So then we default to trying the law of cosines. And that's going to be very helpful, the law of cosines, for finding the measure of side B. Let's have a look. So we've got an angle measure and two sides, and we're missing another side. What kind of ingredients does the law of cosines require? Well, I'm looking at this first one, and I see we need a side length and a side length and a side length. We need all three side lengths. Two of them we're going to use twice, and we need an angle measure. Well, if we had all of those pieces of information, then we wouldn't need to be using this equation, this formula. So if we're missing one of those pieces of information, then this is going to come in handy. So let's see, we need an angle measure and all three sides, but take out one of those. An angle measure we have, but we're missing one of the three sides. So law of cosines is going to work nicely. let's see, and we need, well, we're using angle measure B, so, or we're given angle measure B, so that tells us that of these three options, we should use the second of these formulas because it's the one that says cosine B. All right, so we've got B squared and then A squared plus B squared minus, Sophie, can you remember this? All right, you just whisper it in my ear when the time comes. We've got B squared equals A squared plus C squared. I think it was minus 2AC cosine B. Sophie, you were supposed to remember that. Is that correct? All right, so that's what we need, and then all we have to do is fill in the blanks. So we don't know what B is, so we'll leave the B squared there. A squared is going to be 36. C squared will be 64. Minus 2 times 6 times 8. 6 times 8 is 48. Times 2 is 96. Cosine 32. We can put a little degree mark on there. Now remember that the left-hand side says B squared. So as we, or after we do all this arithmetic on the right-hand side, we'll need to take the square root of that value. This is so easy to type into the graphing calculator that for the first one, I'm going to use the grapher. Or if you have a 2-line entry scientific calculator, that would be easy also. So I've got 36 plus 64 minus 96 cosine 32, enter. And I got 18.587. I didn't make sure that I was in degree mode before I did that, so I hit the mode button and just double checked that I am in the correct mode, and I am. So B squared is equal to 18.587. We'll take the square root of both sides. On the grapher, I hit second and then the x squared button, which gives me the square root symbol. And then I can hit the second button again, and down here toward the bottom right, above the negative sign, it says ANS, and that stands for answer. So it recalls the previous answer of 18.587, but it uses the entire decimal. It uses that exact value and takes the square root of it, and I got 4.311. And maybe I'll write that into my diagram also. Now the good news is, well, the bad news is we still have 2 angle measures that we need to figure out. The good news is we now have a full pair. We have angle measure B and side length B. So we can use that as a full pair as part of, or use it in, the law of sines in order to find our next angle measure. If you're using the graphing calculator, I think you can do this, I'm sure you can do this on the scientific calculator. That's the TI-30XA. I don't know how to do it on that calculator, but I know how to do it on the TI-84 grapher. And what I'm going to do is I still have that 4.311 number on my screen. Where is it? Near the bottom left corner, right above the on button, is a button that says STO. S is in Sam, T is in Tom, O is in ostrich. And it's got a little arrow next to it. And I'm going to hit that button. And on my screen, I get ANS, which is the previous answer, and a little arrow. And then I'm going to hit this variable button that has an X and a T and a theta and an N on it. So now it says answer, and then the arrow, and then X, and I'm going to hit enter. And the 4.311 shows up on the screen again. What I just did in here is I stored that exact value in the variable X, which is going to come in handy in a second. So let's keep going. Oops, there we are. Let's use the law of sines now to find angle measure C. So that is the sine of C over C is equal to, and we're going to use the full pair, so we'll use our B values, the sine of B over side length B. And I don't know what my C value is, but I know that my side length C is 8. The sine of B is 32, or sorry, the sine of angle B, which is 32, divided by side length B, which is 4.311. Now the 4.311 is probably good enough for us, but we're going to end up using the exact value in a moment. Multiply both sides by 8. That gives us the sine C all alone, and on the right-hand side we have 8 times the sine of 32 degrees divided by the 4.311, and then we need to take the inverse sine of both sides, so C equals sine inverse. When I took the inverse sine of the left-hand side, the inverse sine of the sine, those two values or operations canceled out, and this is the inverse sine of 8 sine 32 over 4.311. Let's try this in the graphing calculator. I'm going to type in the inverse sine, so second sine. It opened parentheses for me automatically. I'll type 8 and then hit the sine button, which opens another set of parentheses. I'll type in the 32 for the 32 degrees. I'm going to close the parentheses, divided by, now instead of typing divided by 4.311, I'm going to do divided by x. Close my parentheses again and hit enter. And I got 79.517. And that's degrees. We just took an inverse sine, which returns an angle measure, and that is angle measure C. My C looks a little bit like a lowercase c. I should make it a bit larger. But that is our second angle measure. And now for the great news. And if you wanted to, you could, I don't know, maybe put a little outline around this. This was sort of stage 1. That was one process. Here's a second process that we did. We'll make this one, I don't know if that looks like Georgia or something, maybe. I don't know what state that is. And then we still need to find our other angle measure. Great news is that's really easy because we know 2 of the angle measures. There's the one that's already on the screen of my calculator. I'm going to leave that one on there. There's angle measure B, which is 32. So I'm going to add those together. So I'm just going to hit plus 32. That recalls the previous answer of the 79.51 and adds 32 to it, enter. And then I need to subtract that away from 180. So I'm going to type 180 minus, and then I'm going to do that second answer trick again. So I'll hit the second button, and then my little negative sign down there near the bottom right corner, above which it says ANS. Now my screen says 180 minus ANS, which is 180 minus 111.517. Enter, and I get 68.483 rounded. And in my remaining bit of real estate on the screen here, I'm going to write that angle measure A equals 180 minus, and what we really just did in the calculator is we did minus angle C plus angle B, which works. It's, you know, if you distributed this minus sign, you'd be subtracting both of those angle measures. So this is a fine way to do it, which is equal to, you could write in the numbers if you want to. I'm just going to write down my answer, which is 68.483 degrees. That is angle A. And we have solved our triangle. I think that's all we need to do for that one. Yeah, looks good. Are the angle measures reasonable? Angle measure A is 68. Yeah, it looks maybe a little smaller than 68, but I'm going to let it slide. Angle measure C is supposedly 79 degrees. It looks like maybe a little bit bigger than that, but don't ever assume that your diagrams are drawn perfectly to scale. If it's generated by a textbook like this, maybe you could assume that it's close, or based on the given information, that 32 degree angle does look pretty close to 32 degrees, I would say, and the 6 and the 8. So Angle B is at 32 is pretty small, so side length B is probably going to be your smallest side. And we confirmed that with the 4.31. Side C, measuring 8, is your largest side, so it has to be across from your largest angle measure. We found that C was the 79.5 degrees, and compared to the 68.483 degrees, that turns out to be true. So there is that correlation there to sort of reassure us that we got correct answers. The other scenario where we can use the law of cosines is in the situation where we are given 3 side lengths. And the first thing we'll do maybe is find angle measure A. It doesn't matter which angle we find first, but I'm going to go for A. And let's see if I can remember. A squared is equal to B squared plus C squared minus 2BC times the cosine of angle A. And if you, well, I'm just going to scroll back real quick and double check that. There it is, ABC, 2BCA, ABC, 2BCA. Perfect. All right, so we've got the formula there correctly. It's not worth doing the problem unless you're copying the formula over correctly from a formula sheet, if you're allowed to use one, which my students are, or if you're copying it out of your brain. Let's fill in some blanks here. Well, should we do that right away? We could, but eventually we're going to have to solve for angle A. Maybe before we start plugging in numbers and squaring them and making them larger, we should solve this equation for angle A. That'd be a good exercise. Let's do that. Let's subtract B squared and C squared from both sides. And then we need to get rid of the coefficient on the right-hand side of negative 2BC. So we'll divide both sides by that. A squared minus B squared minus C squared, all divided by negative 2BC. Sophie's nesting in the closet. I was wondering what she's doing over there. Equals the cosine of A. And then we could take the inverse cosine of both sides of this equation right now. We might as well. Cosine inverse of all of this same stuff again. A squared minus B squared minus C squared, all divided by negative 2BC equals angle A. Let's plug in some numbers. Inverse cosine of A squared is 100, or you can write 10 squared if you want, minus B squared is 12 squared, which is 144, minus C squared, which is 16 squared, which is 2 to the 4th to the 2nd, which is 2 to the 8th, 1024, 512, 256. And we're dividing that by negative 2 times 12 times 16. I'm going to do that on the calculator so I don't screw it up. Negative 2 times 12 times 16. I don't love arithmetic. I like the more complicated stuff. Let's try this one in the scientific calculator. If you're using the grapher, you can just type it in. That's not super difficult. If you're typing it in using a graphing calculator, however, I would double up on your parentheses. The inverse cosine is going to give you a set of parentheses automatically. Within that, I would put that arithmetic that's in the numerator, I'd put that in its own set of parentheses, divided by, and then put the denominator in its own set of parentheses. Otherwise, it's not going to work. Try it however you want it. We'll compare answers in a second. So on the single line scientific calculator, we have to evaluate this expression on the left-hand side from the inside out. So I'm going to take 100 minus 144 minus 256 equals, and I got negative 300. I'm going to divide that by 2 negative. So in order to divide it by negative 2, I hit the divided by button, and then I hit the number 2, and then near the bottom right-hand corner, there's a little plus minus button, and I hit that, and you see on the screen that the 2 became negative, so I'll hit equals. So far, I've only taken the negative 300 and divided it by negative 2. Negative divided by negative made the positive. 300 divided by 2 made 150. Now I'll divide it by 12. So I hit divided by 12 equals. I got 12.5. Then hit the divided by button again. Type 16 equals. And I got 0.78125. That number is between negative 1 and positive 1, which means it's in the domain of the inverse cosine function. So we're in good shape. Last thing we have to do on this scientific calculator is hit the second button and then hit the cosine button for inverse cosine. I glanced at it, but I didn't say it. I was already in degree mode. If you need to hit the DRG button in the top row on this calculator in order to toggle your way into DEG for degree mode, please, you should have done that initially. I forgot to mention it. And I got a degree measure of 38.625 rounded. And we've got an A value. Not only do we have an A value, we have a full pair. If you look at the diagram, we now have angle measure A and side length A. So we can switch over and use the law of sines in order to find our next angle measure. And then we'll use subtraction away from 180 in order to find our last angle measure. So there's a rhythm to these problems. The problems where you have to use inverse cosine, or sorry, the law of cosines initially. You use that once. Here we had to find an angle measure. In the previous problem, we used it initially in order to find side length B. And then after using the law of cosines once, we used the law of sines. And then in the previous problem, we did subtraction to find the last missing angle measure. In this problem, we're going to switch over. You use the law of sines, and then use subtraction to find the other angle measure. So there's a rhythm to these. There's a structure. And that structure is something that you want to commit to memory before you go into a testing or quizzing situation. All right, so let's use this pair that we have along with the law of sines. And let's find angle B next. So I will put the sine of B in the numerator over side length B, and then we're using the A as our full pair. So we have the sine of angle A over side A, and we'll fill in some blanks. We don't know angle measure B, so I'm going to leave the sine of B up there. Now, as we did in the previous part of this problem, and by which I mean this part up here, where we solved, all of this stuff, we solved the sort of generic version of this formula for what we're looking for. Previously, we were looking for angle A, so before we even plugged in any numbers, we solved the formula for angle A. In the current part of this problem, we're trying to find angle measure B, so let's use the same format. Let's actually take this version of the law of sines and solve it for angle B before we even plug in any values. We'll multiply both sides by lowercase b. And then I'll take the inverse sine of both sides. All right, so we've really done all of the hard work already. Now we just have to plug in numbers. We'll write them down on paper, and then we'll punch them into the calculator. That certainly can't qualify as hard work. Writing numbers down with paper and pencil, and then punching numbers into a calculator. Side length B was 12 times the sine of, now if I was using my graphing calculator, I would have stored the measure of angle A in my calculator, but since I don't know how to do that on the single line entry, I'm going to use the decimal approximation of 38.625. And then we'll divide all of that by side length A, which is 10. B equals, let's go into the scientific calculator. Now, the angle measure of 38.624 blah, blah, blah is still on my calculator screen. And as I work this solution out from the inside out, I could take the sine of this angle measure that's on my screen. I could do that as my very first step. So I'm going to do that. This angle measure is sitting on my screen. I'm just going to hit the sine button. And I got 0.6242. Then, as the numerator says I'm supposed to do, I need to multiply that by 12. So I'll hit times, and then 12, and then equals. And I got 7.4906. Then I'll divide that by 10, equals. I got 0.74906, which is a number between -1 and +1, which is good because that means it's in the domain of the inverse cosine function. So I will hit my second button, and then the cosine button in order to take the inverse cosine, and I got 41.491. 41.491 degrees. That is rounded to the third decimal place. Putting a box around that. I'm going to take that number, which is already on my screen. I'm going to add 38.625 to it and hit equals. I got 80.1158. I want to subtract that away from 180 degrees. Now that's a little more tricky to do on the scientific calculator. So here's what I'm going to do. Here's what you should do. You should do whatever is most comfortable for you. You might want to take this number and write it down on paper and then subtract it away from 180 after hitting your clear button on your scientific calculator a couple of times. Not a bad strategy. The other strategy that you might want to use is stop trying to be fancy, Newbeck. This was one process that helped us get our second angle measure. Now, instead of trying to do everything in the calculator, why don't you do what we were always doing, which is angle measure C is equal to 180 minus 41.491 minus 38.625, and then just type that into the calculator. Don't have to be so fancy. If you can be fancy confidently, and make sure that the arithmetic is turning out correctly in your calculator, then great, be fancy. I've got this 80.1158 number sitting on my screen. I'm just going to hit minus 180 equals. I know that this number that's on my screen is literally the opposite of the correct answer. It's 99.884. Well, it says negative on my screen, but I know that's not right. 99.884 rounded. And let's not be quite so arrogant. Why don't I type it in? 180 minus 41.491 minus 38.625 equals, hey, what do you know? It's 99.884. So if you want to commit that little trick to memory, you're welcome to. I'm not going to show you why it works, but it works. It's just like multiplying both sides of an equation by -1. That's pretty much why it works. All right, so there are your 3 missing angle measures, which means we have solved the triangle. I'm not going to do this problem because really it's just another side angle side problem. You just have to do this tiny bit of arithmetic in order to figure out that this angle measure right here, which is, you could call it angle C, you could call it angle ACB, you could call it angle BCA, but it's equal to, we could say that angle measure C is equal to 180 minus 35 minus 50 which is 180 minus 50 is 130 minus 35. 130 minus 30 would be 100 minus another 5 is equal to 95. That's degrees. You could fill that into your diagram and then proceed as we did in our first example, which was another side angle side example. I'm also not telling you what the answers are to this question. Work it through using the same process that we did in the first example problem, and then just check to see if your answers seem reasonable. If you get that angle B is equal to 72 degrees, I don't think so. All right? If you get side C is equal to anything bigger than 5, that's probably not right, because then the 2 and the 3 would have to open up so big, it would be too big. They can't open up that far to connect with a side length bigger than 5. So make sure the values you get are reasonable. If you're one of my students, maybe we'll end up doing that one in class. And then I think that moves us into, there's an applied problem here where we want to find the distance across the lake from A to C. This is another side angle side problem. You can try this one also and see if you get reasonable numbers. Bring those numbers to class. Maybe we'll do these ones in class and we'll see if I get what you get. It's tough to come up with an applied problem that seems like a real innovative use of the law of cosines, other than finding the distance across a lake. I suppose that's maybe as complicated as it's going to get. Heron's formula is pretty nice. I actually used this one in real life once in order to determine how much gravel needed to be poured into this like outdoor parking area. It was like a 5-sided parking area. I don't know, maybe kind of like this. And for whatever reason, it wasn't convenient to use it or figure it out like a trapezoid. So we kind of partitioned off a triangular area, and it must have been oblique. So it wasn't quite as regular a shape as this, but we needed to figure out the area of this, and then it was going to be like 6 inches deep worth of gravel. So we actually had to find the volume of gravel that needed to be poured into that part of the parking area. And I was able to use Heron's formula. That was so convenient. And you can imagine everyone else just shaking their head like, of course you would know this off the top of your head. Some things I remember, some things I don't. The value S in this formula stands for the semi-perimeter, which is half of the perimeter. So the first thing we should do in this example problem is find the perimeter. Or let's just find S for that matter. S is equal to 1/2. That's a half. That's a 2, I promise. 1/2 A plus B plus C, which in this problem is equal to 1/2 times 16 plus 10 plus 8, which is 8 plus 5, which is 13, plus the other 8, which makes 21. So it's half of 21. Really? I hate arithmetic. 8 plus 5 plus... plus 4. 8 plus 5 plus 4. No, we have... Oh. I'm getting tired. I don't know if you can tell. Oh, I see what I'm doing. My brain's trying to go in 2 different directions at the same time. Stop being fancy. Just do the arithmetic. 16 plus 10 is 26. 26 plus 8 is 34. Which equals 17. That wasn't so bad, was it? Sometimes simple is just better, okay? And then the area is equal to the square root of, we've got 17 as the semi-perimeter times 17 minus the first side length of 16 times the semi-perimeter of 17 minus the 10 times the 17 minus the 8. This is obviously predominantly calculator work. We've got the square root of 17 times 1 times 7 times 9. Calculator. 17 times 7 times 9 equals, and then I hit the square root button on my scientific calculator. I just took the square root of 1071, and I got 32.73 rounded. 32.73. And just to make sure that I didn't just make an arithmetic mistake because I know that I'm a little bit tired, I'm going to type the 17 times the 7 times the 9 equals. I got the same 1071, hitting the square root button, 32.73 rounded. Looks good. And it's a good thing too because I need a nap. Must be getting old. It's like 9:45. I gotta go put my feet up. Right, so that is it. Is that it? Is there another page? There's another page. Let's do one more problem. You gotta keep your eye on me though, because as we know, I'm getting dangerously tired. We're finding the cost to the nearest dollar of a triangular lot that has these measurements and is priced at $4.50 per square feet. So we need to figure out how many square feet are in the lot, and then since it's priced at $4.50 per square foot, we'll have to take the total number of square feet and multiply it by $4.50. So first, let's find the semi-perimeter. That's equal to 1/2 times 320 plus the 510 plus the 410. I'm going graphing calculator on this one so that I can type in, ooh, my battery is low. Charging the battery is recommended, it says. Very well. Calculator is so bossy. I'm typing in 0.5 and then opening a parenthesis, 320 plus 510 plus 410, close parentheses, equals, and I got 620. So that's our semi-perimeter. And then the area is equal to the square root of 620 times 620 minus 320 times 620 minus the 510 times 620 minus 410. If you want to just type this in from left to right exactly as it appears into your graphing calculator or two-line entry scientific calculator, you're welcome to do that. I'm going to do a little bit of preliminary arithmetic. I think that I can handle it in my head. There's the 620. There's 620 minus 320. Even I can do that. That's 300. And 620 minus 510. Yep, I can handle that one also. And 620 minus 410. I can even do that one. Any of that arithmetic you're not comfortable with? Keep using your calculator. You could do all of this with a 4-function calculator for that matter. All right, in the grapher, I can type second and then the x squared button, which gives me the square root symbol. And then I'm just typing it in from left to right. 620 times 300 times 110 times 210. I'm just confirming all that looks right. I know there's no typos. Enter, and I got 65,548. That's a lot of square feet. You could put the 0.46 maybe at the end. And that's square feet, be careful. SQFT for square feet. And then cost is going to equal area. And I'm going to put area and then feet times price, which is in dollars per, oh, area was actually square feet. We could do FT squared. And then price is dollars per square feet. And I'm doing this to illustrate the, what do you call it? It's like a unit analysis. Ooh, geez. Draw my calculator, sorry. The unit analysis, which I find helpful sometimes. Notice that square feet here and square feet here are going to cancel, leaving us just with the dollar sign, which makes sense because we're solving for cost at this point. So we want our final answer to be in dollars. So I'm going to take the area, 65,548.46, and I'm going to multiply that by the price per square foot, which was $4.50. And that is equal to, I still have my number of square feet up on my screen, except it's an exact value. So my screen actually says 65,548.45536. I'm going to type it in exactly as I've written it on the screen so that our final answer matches up with what's written on paper. So there's the 65,548.46 and then times 4.5, and I got 29. Is it 29? No, it's $294,968.07. Make sure your decimal point there looks like an actual decimal point. We'll put a little dollar sign on there, a little box around that answer. And now we're done. Thanks for sticking with me on this one. Not super difficult, but good to see the relationship between the law of sines and law of cosines and when we're supposed to use the two of them. And in fact, in I think every one of the law of cosines problems that we just worked, in order to fully fill out the triangle, or in order to totally solve the triangle, after using the law of cosines, we switched over and used the law of sines also. So on a quiz or a test, you might need to bring both of those formulas to bear. If you haven't already, please like and or subscribe. I would appreciate it. I'm not making any money from this, so a comment or a like or a subscribe would be awesome. Thank you so much, and I'll see you next time.